Math 1314, section IC1, spring 2022, Tyler Junior College, section 5.4, linear equations in two variables. Video 2, the slope of a line. Several of you may already know something about slope. When I teach this class face-to-face, I start by asking, what's anything you know about slope? And I hear a lot of things that are usually correct and all over the place. So at the end, we tie it all together in a nice little package. So I want you to stop and think for a moment. What do you think you know about slope, either from an algebra perspective or from a non-algebra perspective? Where have you heard the word slope before? So think about that. Think about it in terms of, oh, I remember slope in a math class. Slope means this. Or outside of maths, when I hear the word slope, I think of such and such. So think about those things for a second. Now, if there's any of the math things you remember about slope, you will probably see it either in this video or the next video or a few more videos down the road. But the concept of slope is actually pretty straightforward. However, when I ask my algebra students, calculus students, beyond calculus students, what is slope? They'll give me a lot of things that are mathematically correct, but the one thing they never give me is what the idea of slope actually is. In other words, what does slope actually measure? Well, here's what slope measures. Slope is a measurement of the steepness of a line. So whenever you measure a slope, calculate a slope, observe a slope, whatever, you're looking at a number whose job is to measure how steep a line is. Now, you see three lines in front of you. The first one is a horizontal line. The second one's moving upward from left to right. And the third one's moving upward, but at a steeper grade, if you will, a steeper slope. Which of these lines do you think would have the greatest slope? The first, the second, or the third? Well, if we're measuring how steep a line is, it would make sense that the steeper the line, the greater the slope. So the one on the right would actually have the greatest slope. This one has the greatest slope of these three. Now, which one do you think would have the least slope, meaning the number that describes how steep a line is? Well, which of these lines is least steep? Well, that would be the horizontal line on the left. This one would have the least slope. And again, among these lines, of course, the one in the middle would have somewhere in between. But how do we actually measure this? How do we measure how steep a line is? Now, you could start breaking out some geometry and talk about angles. For example, the leftmost line, if you were to stretch it, makes a certain angle with the x-axis. The middle one, if we were to stretch it, makes a smaller angle with the x-axis. And the first one doesn't even hit the x-axis. So there's a geometric perspective in terms of measuring angles that's associated with describing the slope of a line, but this is in a geometry class. So we're going to describe the slope of a line using a different measurement. What we're going to do is compare how far we have to travel horizontally with how far we have to travel vertically, or rather the other way around, to get from one point on the line to the next. For example, let's say I start here, and let's just say that this point is, oh, it looks like it might be 0,2. And then I go over 2, and then I go up 3. I don't know how accurate this is. I'm just making these numbers up. At what point would that put me at? Well, it would put me at 2, not 2,3, because the first point was already up 2, and then we go up 3 more, would put it at 2,5. We could measure the slope by comparing how far we had to rise to get to the second point to how far we had to run horizontally to get to that point. So we could say that the slope here would be 3/2. For every 3 that we go up, we have to go 2 to the right. Now, let's say we did the same thing over here. And let's say that this point is 0,2. And then we go out to this point way over here, which is only up 3, but it looks like I have to go over like 4 or 5. Let's just say over 5. Well, to get there, to get from 0 to 5, we have to go over 5, But to go up from 2 to 3, we only have to go 1. So we could say that the slope of this line is how far we went up, which is 1, compared to how far we had to go over, how far we had to run, which is 5. Now, if we did the same thing over here, like for example, let's say that the y-intercept here is 0, 2, and let's say we went over 5. That would put us at the point 5, 2. What would the slope of this line be using the same concept? Well, we would go over 5 because we went from 0 to 5, but how far up would we go? 0. So we could say that the slope over here is we went up 0 after going to the right 5. Of course, 0 over 5 is equal to 0. But if you think about it, that makes sense to say that that horizontal line has a slope of 0 if the purpose of slope is to measure how steep a line is. What, you're not steep at all? Well, then your slope should be 0, and it is. Now, there's two concepts for viewing how to calculate a slope. Slope definition number 1. Slope is the ratio of rise to run from one point to another on a line. Let me explain what I mean by that, and then we'll talk about the second sentence. When we have a line on a coordinate plane, in other words, we got an x-axis and we got a y-axis, and we have some sort of line on there. We'll make the line in pink. That seems to be the color of my lines this morning. Now, technically, this line goes forever, so maybe I should use a double-headed arrow to draw it. There we go. So we got this line, and we want to measure how steep it is. Well, we can compare the run to the rise, or rise to the run, excuse me. And what I mean by that is if we pick any 2 points, we'll say this one and this one, and we measure from the first point how far we have to travel horizontally and call that the run, and then how far we have to travel vertically and call that the rise, we can define the slope. And my apologies, I think I did something back here I didn't mean to do. No, I didn't. I haven't done it yet. We can define the slope as the ratio of rise to run. So consider that a definition, if you will. I think it's more of a concept. This is how we decided to measure the slope of a line, by picking 2 points and seeing how far we have to rise compared to how far we have to run when we go from one point to the next. Now, it is worth pointing out that the 2 points are irrelevant because similar triangles have proportional sides. Well, what does that mean? Well, to kind of show you what I mean, let's say that I use the same ending point, but so this point here, but I go twice as far in each direction and I land over here. So in other words, when I run, this run is twice as long as the other one. So I'm just going to put a capital run for that. And this rise is twice as long as the other one. Well, the two triangles that are drawn, the blue triangle, well, 2 of the 3 sides of the triangle are blue. There's the third side that's blue. And the green triangle, again, if we draw the third side here, those triangles are what are called similar. And without getting into geometry too much, it basically means they're the same shape, just different sizes. Almost as if we zoomed in on the blue triangle and it blew up to look like the green triangle. When you zoom in and out of a picture, the relative size of an object may change. Excuse me, the absolute size of an object may change, but the relative sizes don't. What that means is, for example, in the blue triangle, if the rise was twice as long as the run, then in the green triangle, its rise will be twice as long as the run. So when I form their ratio, I get the same ratio. It would just reduce to an equal fraction. But that's why it doesn't matter what 2 points you pick, because of similar triangles. So pick any 2 points, figure out the run, figure out the rise, compare rise to run, and then you have your slope. Let's take a look at a few examples. Now, before we say anything, which of these should have a slope of 0? The third one, it's a horizontal line. We're measuring steepness. But I got another question. Of the other two, the first and the second pictures, one of them has a positive slope and one of them has a negative slope. Do you know which one will have the positive slope and which one will have the negative slope? We'll answer that question in a minute after we actually calculate the slopes. Now, to calculate the slopes, we have to know how far we go horizontally. You know what? I've got a single arrowed line, a single-headed arrow I can draw here. Don't know why I wasn't taking advantage of that earlier. In order to calculate the slope, we can figure out how far we run and how far we rise to get from one point to the next. Let me write that a little bit better. Now, sometimes it might be obvious. For example, in this picture, the first point is at 0,2, and the second point is at 5,3. So how far did we travel in the x direction? If it's not obvious, look at the x coordinates. The first x coordinate was 0. The second x coordinate was 5. So to go from 0 to 5 is a space of 5 units. So we went 5 to the right. How far up did we go? Oh, that one's pretty easy to see because the first point was up 2, the second one was up 3. So we had to go up 1 more to get from 2 to 3. Or we could just subtract 3 minus 2. And so the slope over here is 1/5. Now I'm going to introduce a new letter to you. If you just had to guess the letter for slope, you would probably never guess M. I think it has to do with the French word for mountain, or to climb a mountain, monter. But in general, whenever you see the letter M in an algebra class, it's the letter for slope, because that makes perfect sense. Slope starts with S, so we're going to use M to represent it. So our slope is 1/5, rise over run. But what about the second picture? On the second picture, if we start at the point -2, 3, we would have to run to the right a certain amount until we're above the second point, and then turn and quote unquote rise to go to the point 1, 0. And the reason I said quote unquote rise is because we actually went down instead of up. Now, when that happens, it's still called the rise, even though it went down. The run is how far we have to go to get from x equals -2 to x equals 1. Well, how far apart are those? How far do I have to travel this way to get from -2 to 1? It might be easy to see that it's 3 just by marking up the x-axis, but there's got to be a better way to figure out how far it is to get from one number to another without counting spaces in between. But regardless, the run is equal to 3. Now, the rise is a little bit trickier, because when we say rise 1, we expect to go up 1, but we're going down. What can you say about the rise if we have to go down instead of up? And the answer is the rise should actually be negative. We started at an elevation of 3 and then went down to an elevation of 0. How far down did we go if we went from 3 down to 0? Well, that should be pretty obvious. We went down 3. If you just say rise equals 3, then you're telling me that I went up 3. To say I went down 3, you stick a negative on it and still figure out the slope as the rise, which is -3, over the run, which is 3. And in this case, we get a fraction that not only reduces, but it flat out divides. -3 divided by 3 is -1. The slope of the second line is -1. Now, earlier, if you said the first line had a positive slope and the second one had a negative slope, then you've got a good intuitive feel about what it means for a slope to be positive or negative. But in general, if a line is increasing from left to right, I hope that looks right from your perspective. If it's increasing from left to right, then it will have a positive slope. But if a line is decreasing from left to right, then it will have a negative slope. And as far as the last one, well, its slope's going to be 0. Why? Because if I run from the first point to the next, I would run, well, let's think about this. I'm going from -2 on the x-axis to +3 on the x-axis. How far apart are those? Well, they're 5 apart, which you could find by 3 minus -2. But the run is equal to 5. But we did not move up or down any, which means the rise is 0. And so the slope would be 0 over 5, which of course is just equal to 0. But then again, we've kind of already said that any horizontal line will have a slope of 0. So that's one way to think about slope graphically, where you draw a line, or you have a line with 2 points on it, and then you calculate how far you run, calculate how far you rise, except if it's going down, it's a negative rise, and then slope is the ratio of rise to run. But there's a second way to think about slope. Slope definition number 2 answers the question, if you tell me the 2 ordered pairs, can you find the slope without drawing the picture? And the answer is yes. If a line passes through the points x1, y1 and x2, y2, so 2 generic points, then the slope of the line is given by the following formula. I'll show you the formula in just a second. By now, you should learn that I don't always just put everything out there, but I want to justify this formula by attempting to draw a generic picture with generic points on it and try to play the rise over run game. If this first point is x1, y1, subscripted with 1s to mean the first point, and the second point is x2, y2, we can still calculate the slope as the rise over the run. But how can you represent the rise and the run generically? Here's the run, and here's the rise. Well, the run is how far you have to travel to get from the first x to the second x. And if you were paying attention in the previous examples, I kept mentioning that you could figure out how far you travel by subtracting the second x minus the first x. And we could do the same thing for the rise. We could figure out how far we rise by taking the second y and subtracting it from the first y. So we could still figure out slope as rise over run, but now we can write it like this. To find the slope, excuse me, that was supposed to be a drawing, not a rectangle. To find the slope when you know the 2 ordered pairs, it's still rise over run, but listen closely, there's a very subtle rhyme here. To find the rise, subtract the y's, second minus first. And to find the run, subtract the x's. I can't make that rhyme. To find the run, subtract the x's. And a lot of people recognize this formula as the quote unquote slope formula, because it's like a recipe that says, give me 1 ordered pair, give me another ordered pair, and I'll do this to it, and I'll give you the slope. So it is just rise over run, but it more explicitly says, this is how you calculate the rise and the run. To find the rise, subtract the y's. To find the run, subtract the x's. It is important that you're consistent with the order. Whatever you call the second y, be consistent and call its x the second x. We're going to work 4 examples, and that'll be the end of this video. Find the slope of the line that passes through the following points: 3, 7 and 7, 17, and -1, 2 and 3, -3. I invite you to pause the video and see if you can calculate the slopes, but at the end, I'm going to ask you, what do these slopes mean about these lines? So go ahead and pause the video if you haven't already. Hopefully you tried them, because here we go. To use the slope formula on 2 ordered pairs, what I would recommend, until you're super accustomed to it, is to start by writing the actual formula itself. Then going to your ordered pairs and labeling your x's and y's. Call the first x x1, and the minute you label that, everything else has been set, because its y has to be y1, and the other ordered pairs x is x2, and the other ordered pairs y is y2. When you set up the slope formula, I highly recommend writing the fraction bar and the 2 minuses before plugging any numbers in. The second y is 17. The first y is 7. The second x is 7. The first x is 3. Our formula says it's going to be 17 minus 7 over 7 minus 3. Well, 17 minus 7 is 10. 7 minus 3 is 4. Our slope is 10/4. You will be expected to reduce. That fraction reduces to 5/2. Now, the other one, you got to be careful because of all the negatives. I would still label the x's and the y's. First x, first y, second x, second y. And if you're thinking, I don't want to waste time writing that, I'll tell you right now, the most common mistake people make with this formula is putting the numbers in the wrong place. So it is worth your time to prevent that from happening. You can do that by labeling the x's and the y's carefully, and then setting up the formula with the fraction bar and two minuses before plugging everything in. I would still recommend having the actual formula somewhere nearby to look at. It's over here on the first one, so I don't need to write it again over here. I can just look over there. But I would be very methodical about the setup, because after that, everything's pretty straightforward. Now, in this one, you got to watch out for your negatives. The second y is -1. The first y is 2, so that one's not too bad. On the x's, the second x is 3, but the first x is -1. Now, if you just write this, it's wrong. I wrote the 1, there's already a negative in front of it. Well, guess what? This minus is part of the formula. This minus is part of that 1. If you only put 1, you're losing one of the two. The first x is -1. It goes after the second subtraction sign. Now, naturally, when you stick negatives inside of a subtraction problem, there is a possibility of coming up with a double negative, like on the bottom. On the bottom, we have a 3 minus a -1, but that becomes a 3 plus 1. And of course, 3 plus 1 is just 4. Now, on the top, we have -1 minus 2. Well, when you're combining two negative numbers, you just get a bigger negative number. -1 minus 2 is -3. This fraction can't be reduced, and so our slope is -3/4. And now for the question I asked a minute ago. Based on these slopes, can you tell anything about these lines? Hint, it's whether or not the slope is positive or negative. Well, when the slope is positive, that means your line is increasing from left to right. And when your slope is negative, that means your line is decreasing from left to right. It's kind of convenient to observe these things, because eventually we're going to be drawing the graphs of these lines. And in advance, if we just make a mental note that this line should be increasing or this line should be decreasing, and it ends up not being, then that means that we've caught a mistake, because we anticipated what we were supposed to see. All right, let's do 2 more and then we'll call it a video. Find the slope of the line that passes through the following points. Let's raise this up a little bit so we have as much room as possible without me obstructing any of the words. There we go. All right. Again, I invite you to pause the video and see if you can find the slopes of these two lines. I will warn you that both of these have subtle issues, one a lot worse than the other, so to speak. But pause the video and give it a try. All right, did you pause the video? Why not? If you did, great. Here we go. Let's start by writing our formula again. To find the rise, subtract the y's, second minus first, and it could be first minus second, as long as you're consistent. If on the top you put y1 minus y2, then you would have to put x1 minus x2 on the bottom. Just make sure that the order of the subtraction is the same on the top and bottom, and it really doesn't matter whether it goes 2 and 1 or 1 and 2. And I would take the time to label first x, first y, and second x, second y above the ordered pairs. Because, and again, I said it before and I'm going to say it again, the most common mistakes people make here is putting the numbers in the wrong spots in the formula. So be very meticulous about it and then finish it off. All right, we're going to put the second y on the top subtraction problem on the left. Second y is 8 minus the first y, which is also 8. And on the bottom, second x is 5 minus the first x, which is 2. And now we can just subtract. 8 minus 8 is 0. 5 minus 2 is 3. 0 over 3 is 0. The slope of the first line is 0. Oh, wait a minute. What does that mean about the line? If slope is a measurement of steepness and your steepness is 0, what kind of line are you? You are a horizontal line. And that would be easy to see because we could draw this picture really quickly. 2, 8 is over 2 up 8. So we'll say it's right there. And 5, 8 is over 5, but also up 8. And if we connect those, we get a horizontal line. So keep that in mind. File that under things to know, that if the slope is 0, means horizontal line. Wow, that's just horribly spelled for multiple reasons. Horizontal line. So slope equals 0 means horizontal line. Let's take that font size down a notch and some close parentheses. All right, so, and you can spot a 0 slope a mile away because the y coordinates match. Notice in these two ordered pairs, they both have the same y coordinate. That predestined them to be on a horizontal line, and hence their slope was 0. But what about D? Have you tried to find the slope on part D yet? Don't need to write the formula. I can see it under part C, but I will set up the empty formula, and I will label my x's and y's. X1 is 3, Y1 is 10. I'm sorry, X1 is -3, Y1 is 10. X2 is also -3, and Y2 is 15. Filling in the formula on the top, second Y is 15 minus the first Y is 10. And on the bottom, second X is -3, and the first X is also -3. On the top, we get 15 minus 10, which is 5. But what do we get on the bottom? On the bottom, the minus minus becomes a plus. So we end up getting -3 plus 3, but that's equal to 0. What's 5 divided by 0? If you said 0, you would be incorrect. Get out a calculator and try it. And then it should tell you either error, undefined, domain error if you want to get nitpicky. But regardless, when you have a fraction with 0 on the bottom, that is undefined. So what is the slope of this this line? Well, there's two correct ways to say it. You could either say the line has no slope, or you could say the slope is undefined. I prefer saying the slope is undefined, because if you say the line has no slope, which is technically correct, you might accidentally think that that means its slope is 0, which is a different thing. So the slope is actually undefined. Let's summarize what just happened here in terms of slope being 0 and slope undefined. Line slope is 0. Let me bump up the font size. If and only if the line is horizontal. Where'd my cursor go? There it is. So a line slope is 0 if and only if the line is horizontal, which means if the slope is 0, then the line is horizontal. And if the line is horizontal, then the slope is 0. But what does it mean for a line slope to be undefined? A line slope is undefined if and only if the line is, what do you think? Well, we have an example back here. -3, 10, and -3, 10, and -3, 15. If we were to draw that real quick, -3, 10, -3, 15, we don't need any space below the x-axis. -3 is back here. And let's scale by 5 since we're going up 10 and 15. 5, 10, 15. The 2 points we had on the last example were -3, 10, -3, 15. The 2 points are directly above each other. So when we connect them, what kind of line do we get? We get a vertical line. So a line slope is undefined if and only if the line is vertical. Not sure how I got up there. Which kind of makes sense if we're attempting to describe steepness. Remember, the steeper a line, the greater its slope. So what should your slope be if you have the ultimate steepness? You're perfectly vertical. Well, as the line rotates up, its slope gets closer and closer to infinity. And technically, when you get this way, you could say it has an infinite slope. There's something technically wrong with that. So we just say the slope is undefined. All right, I think I've shown you everything about calculating slope that I want to show you. In the third video, we're going to talk about the actual equation of a line relative to its slope and to its y-intercept. I wonder what you call the form of a line that includes the slope and the y-intercept. Bet you've heard this story before.